let's see a little bit more about that integrable word. All right. If our function is integrable, that means the integral exists. Okay, a lot of words that sound the same there. When the integral exists, we say that the function is integrable over the interval. So there's a tongue twister for you. But if our function is non-negative, that means all the values are 0 or higher, okay? And integrable, so our integral actually exists on the interval a to b, then the area under the curve of f of x from a to b is determined by the definite integral. Okay, so we would write that as saying that the area actually equals the result that we get from doing a definite integral. So a to b f of x dx. All right. Cool. And the rationale behind that, why we're able to say this, is because of that Riemann sum idea behind the integral. So the rationale is that we took a Riemann sum, okay, which, if you'll recall, Riemann sums were what we used to add up the areas of a bunch of little rectangles in section 5.2. So we took a Riemann sum of the areas of n rectangles. And if n is like, you know, a finite number of rectangles, like if n is 4 rectangles or 10 rectangles or whatever, that will approximate the area under our curve. So we can get an approximation of that. Okay, so we were adding up a certain number of rectangles. But now we have let n go to infinity as part of the integral definition. Okay. Integral definition. Okay. So let me go back up to that definition real quick here. All right, so this part here, this alone is the Riemann sum. And so you're adding up, again, these are areas of little rectangles. This is the width times the height of each little rectangle. And then we're adding up n of those rectangles. Okay, where n is, 4, 10, 100, whatever. Now for this definition, we tacked on this extra limit in the front. Limit as n goes to infinity. So that means your number of rectangles is going to infinity. And we could see, especially with the computer simulation there, we were able to see how much more accurate of an area estimate we could get by using more and more rectangles. And now we are using the most rectangles. We're using an infinite number of rectangles. So we're going to be the most accurate and actually come up with the real true area underneath the curve. All right, so it's pretty cool, actually. Yeah, we add up a bunch of rectangles and then we let the number of rectangles go to infinity. All right, so that's why we're able to say this. Okay, this finds the actual area. Okay. Now, this is a good equation right here. Notice one little thing though, in this kind of condition statement beforehand. This says if f of x is non-negative, that's a real specific type of function there. So for f of x to be non-negative, all of the values for f of x need to be greater than or equal to 0. And we know that's not always true. In fact, often not true. A lot of functions can have negative values, you know. So we want a more general definition for what this integral will get us. And that is right down here. The more general version of this is looking at something called net area. Okay, so in net area, we consider areas beneath the x-axis. Those are going to count as negative area. Okay, which is a little bizarre, and try not to think about this too much in like real world physical terms, because in real world physical terms, we don't really say the area can be negative. This is just a mathematical definition here. All right, so if you had a function, say, that had some negative y values to it, so let's say here's our function x versus f of x, and your function went something like this. Blech. Okay, and you were trying to find the integral from a to b, doing something like that. Okay, so the actual area we'd be looking at would be this between the curve and the x-axis, and then also this part down here between the function or curve and the x-axis. But this area up here would count as positive, and this area down here would count as negative area. So actually, the way I've drawn that, the two of those would probably just kind of cancel each other out. Or we might even have a little more negative area down there than positive. So yeah, that's the idea here. I'll kind of shade this in, that way you guys can see what that negative area is. And then this is positive up here.